Hi everyone, welcome to Weekend Upskilling. So we are starting off a series for system design. Before moving on to how the systems are designed and what are the tech stack and how the architecture is around that those systems, let us go through some of the very key concepts or very key terminologies that we will come across this system design series. The very first thing to start with is scalability. When it comes to scalability, there are two major categories of scaling the systems. One is vertical scaling, another one is horizontal scaling. Vertical scaling is about giving more power to your server or computer, and horizontal scaling is like adding more servers or computers or nodes to the architecture. Why we do vertical scaling is as in when the core logic or the business needs more power in its computational models, which might not be served by the previous servers. Say, suppose previous server was an 2 GB RAM with two core CPU server, which might not be able to perform certain tasks. So there is a necessity for us to upgrade the system from say 2 GB RAM to an 8 GB RAM module and a two-core processor to an eight-core processor for serving certain complex computational business logics. So that is when we'll go for vertical scaling. This is so when it comes to horizontal scaling, it's about adding more units or more servers or nodes to the architecture. Say suppose you need to say scale the system to serve 1,000 requests from a starting point of 100 requests, wherein previously you were serving 100 requests per second, but now you'll have to serve 1,000 requests per second due to some business needs. That is when we'll go ahead and scale it horizontally, wherein if suppose a single server is able to respond to 100 requests in a matter of a second, then we'll scale it up to 10 servers, so that 10 servers each will handle 100 different requests, wherein 100 into 10 will be 1,000 requests served in the given second. So this is one of the scenario where we will do go ahead and scale it horizontally. So the next key terminologies that we will come across is security and privacy. Securing our systems with authentication, authorization, or encryption or privacy. Say, suppose you go to the Gmail and give your email ID and password and log into the system. That's when you will be authenticated to log into the systems. Says another thing is like authorization. Say there is a food delivery app. A customer might have a different app in the Play Store, and the delivery agent might have a different app in the Play Store, and the hotel owner might have a different app in the Play Store. But however, all of these front end apps might be integrated at the back end with similar or shared services regarding customer information, hotel details, and the delivery partner details. So which which user can view what, and which user can update what or delete what comes under authorization. Say delivery agent might not be able to see certain details of your order, and hotel owner might not be able to see certain details of the consumer or the customer. And maybe the customer might have all the information about the delivery agent and where he is, and what he is bringing in, and what kind of hotel it is, and what is their rating. So all these kind of different roles and the permissions required for these different roles are covered under authorization using different techniques. Then when it comes to encryption and privacy, the we might have the databases stored under secure proxies and firewalls and under secure username and password, but still there could be certain places where the data need to be encrypted. When it comes to your when you the classic example is when you see most of the e-commerce site which saves your card does not save the complete card directly as in the 16-digit card number. Instead they will encrypt the first 12 digit and save just the last 4 digit directly. So the first 12 digit might need certain techniques to be read, and it would be like within the system to system it will be able to read the details, but which might not be immediately visible to the human eyes. um, so this is called encryption. For encrypting say rather than the first 12 digits of the card, might be associated with its own different set of string, maybe in an alphanumeric fashion, and get stored in a different column of the table, and the four digit will go into a different column which will be human readable. So for to do this, like we have different techniques to transform the data, like be it TLS algorithms or AES algorithms, and we have like n number of algorithms to do it. This comes under encryption and privacy. So the next thing in system design is all about measuring the performance of the system. This is done to make sure our system will be able to serve the load or traffic in a given period of time. So we do consider multiple factors in when it comes to measuring the performance of the system. However, two major things which we account for is the latency and the throughput. Latency is the time delay between the time taken for the server to respond to a particular request. Say you do a login, the server takes like 0.2 milliseconds to authorize your login by validating your credentials against the encrypted data, and match your password and say, hey, yes, this is a valid user and he can log in. This is the password of this particular user. All these business logics are applied, and the server responds within 100 milliseconds. Then the latency for that particular request is measured to be around 100 millisecond. Latency is like nothing but the time taken for the server to respond to your request. Then throughput of the server, or throughput of your complete architecture. Say suppose you have like 100 servers, but out of the 100 servers, like one particular server is able to respond for 100 different requests within 1 second of time. Then we can say it has an throughput of 100 per throughput of 100. So we measure it in terms of seconds in most of the systems. Yeah. So 10 different servers or 100 different servers. So be it 10 different servers. So then each server is capable of responding to 100 requests in a given time. Then your overall architecture's throughput would be 1000 TPS. So the next one is networking and communication. When it comes to networking and communication, we use multiple different protocol layers to communicate, and there are different communication mechanisms as well. So when your application sends some request to the internet, it travels all the way through the internet, and then takes a particular IP where the request would be serviced. And to complete this transaction, there are like multiple layers which go inside. Let us have a detailed walkthrough around how this happens in a separate video. And however, like we have different communication mechanisms like HTTP, HTTPS, TCP, or IP, based on which the communication happens. It's mostly the rules and standards for data exchange. And then when it comes to communication mechanisms, there will be client server model or publisher subscriber model, wherein there will be some kind of, or wherein like we might have an client who will be sitting with a laptop, or there will be an API which will make a request and get the response back, or there could be certain subscribers who will have their listeners open to listen for certain messages from the publisher, which will come by a machine broker. This is how the request and response models are designed. Yeah, this we will come across during the event based architecture. So moving on, we have the availability. So it is about having the redundancy and high availability. Like when it comes to redundancy, instead of having a single server, even if your system or if your service is very small and it does not require to serve much TPS. It can be very well managed with one single server. Still, we will go ahead and have two different clusters and two different servers deployed and the traffic routed between both of this, to make sure if either one of the server goes down, the other server is still live and is able to serve the request to avoid any single point of failure. Next one is high availability scaling. Say um, instead of putting all your business logic and code into one single service or one single layer and start serving the request from there. Instead, say a classic example is microservice architecture, wherein every single component is divided. Say when it comes to an e-commerce website like an Amazon, user related information will be served by different service layers, and cart related information will be serviced by a different service layer, and checkout will be handled by a different layer. So at a given point in time, if any one of the service fails for just few milliseconds or few moments, until when the next server comes and backs it up, we will not have the entire website down. Meaning, maybe a particular set of users who were trying to log in might be affected because login service was down for a couple of minutes, but no other layers of the business will be affected. So by this way, we will ensure like we are up and our site is running for most of the 99.99 percentage of the time with very minimal operational failures. This is high availability. So next we have rate limiting. This is like more about controlling the resource access or preventing misuse. Say suppose a general or a regular user who is genuine accessing your website or accessing your API contacts or services might be sending up 10 or 12 requests per a minute or per some given X amount of time. But say suppose there is a hacker who is trying to hack your systems or do a bot attack on your systems. He or she might be trying to send 1,000 requests per second or within milliseconds using their bot algorithms or hacking algorithms. So, to identify and stop this kind of hacking or any kind of suspicious activity in our business, we have rate limit. We have different set of different techniques to do the rate limiting, based on which either like say suppose we might see the IP from which the request is coming from and try to stop that particular IP or block that particular IP for a given amount of time. If we find a suspicious activity from that IP, so this is called rate limiting. This is just to prevent the misuse or bot attacks or the hacking into the systems. There are multiple different techniques and algorithms to identify it, like token bucket mechanism or leaky bucket mechanism. We'll get into these things in detail as and when we go through deep into these topics. Next one is the reliability. How reliable your system is. We have multiple techniques to make sure our system is reliable. One classic way is, say suppose you have a DB which has like millions and millions of users PA information or their order summary on what they have purchased. Instead of having a single DB, we will try to have different copies of the information in multiple different DB nodes, so that if any one of the copy has an issue, our system will be able to pull the next copy and still make sure our services are up and running. This is about first one is the replication. I was discussing about replication. This is about creating multiple copies or multiple servers or multiple nodes of the server, or keeping two different two different clusters, to make sure there is no single point of failure or nothing goes wrong when one of the server or one of the DB crashes or gets corrupted. The next one is failover mechanism. Say some suppose so failover mechanism is one of the subcategory of replication. Say you have replicated, but you should know when to use the second copy. Say your system generally serves 100k request, and out of 100k request, 99% of their request response with 200 success. Okay, but we might have certain scripts which will monitor this one, and if you find the number of 400s or 500s going up from 1% to 10 or 20, then we will come to know there is something suspicious going on, or something got corrupted in your DB or your server. Then the failover mechanism will detect and start routing your traffic to the different servers or different DB nodes. This is just to this is just an uh, transfer of the requests from one layer to another when we find the first layer has some issues in it. Asset transactions, this is more about this is ensuring the data or DB is operational and functional to its fullest. The very first thing is very wherein the A stands for atomicity, C stands for consistency, I stands for isolation, and D stands for durability. When we say atomicity, say suppose you are making a payment from one of your third party apps. In this, there would be multiple layers involved. Say the request would go from your mobile device to the bank's initial layer or common pool, and then from there it will be routed to your individual account balance. It would check certain things and then detect the amount from your account, and then the third step is it will send the amount to uh, the business where you have made the purchase or made the payment, and then the business has to confirm that their payment is successful, and then it has to be confirmed that it will be made an entry in your DB, and then you will get a success response back to your mobile screen. So over here, to maintain atomicity, we will make sure the entire transaction is completed, and if at all if anything fails, then the all the changes that has happened in the middle layers will get reverted. Say suppose the amount has been deducted from your bank account, but it has not reached your not reached the business where you tried to make the purchase. Then the transaction will be marked fail across all the systems. Though it has been detected from your bank, it will get reversed. So this property is called atomicity. The next thing in asset transaction is consistency. Say suppose you are trying to you are sitting in United States, and your bank account has your account balance being calculated in dollars. But you are trying to access some website in say suppose Europe, like, and where the transaction is happening in euros. When you try to make the payment, even though there are like multiple layers which has somehow by some way it has permitted this transaction, but still database holds the responsibility of not allowing this by making sure the transaction is carried out only in dollars, and you will not be allowed to pay for a transaction that has happened in euro via dollars. So to maintain this, like, there will be consistency or different set of rules which will be maintained in your DB layer to detect the anomalies. A row wherein your balance is measured in dollars cannot accept a transaction in euros. This is consistency, and then isolation and durability are more about making sure there are like making sure the data that is stored in the database has been committed and will withstand the failures. This will be achieved using like multiple different techniques to withstand the failures. So when it comes to consistency, it is about users having the same behavior across the systems. There are places where we will need strong consistency, and there are places we will be okay with the eventual consistency. Here one of the key factor is like the trade-off. We can argue that all the systems can have strong consistency, but we might see we might see the difference in the speed, or the difference or drop in the latency. Over here, this is more purely about the business trade-offs and the call which we make. Say, for example, the retrieval of bank balance might need a strong consistency. By which what I mean is you have logged into your bank account from your mobile and a web browser, and from mobile you are making a transaction to a person. Say initially you had 1,000 rupees, and you are sending 100 rupees to a person X, and this transaction is successful. But when you look at the web browser, there could be some way which the web browser is immediately able to pull the information and display the balance as 1000, sorry, 900, not 1000. So these are one of some of the areas, or this is an example where we need strong consistency. Eventual consistency are the places where, in a distributed environment, we are okay with a slight delay. One classic example is about a social media feed. Say you upload some information to your Instagram account, and there is a slight delay in the information to get it propagated to your friends or your followers list, with few seconds of delay. This kind of delays, when it is acceptable, we will go for eventual consistency for X number of reasons. So moving on, we have data storage and retrieval part of distributing, copying the data for the performance and reliability. There are multiple ways, multiple different techniques, and the famous or classic ones are partitioning, sharding, or replication. Partitioning is uh, partitioning or sharding is where, say, suppose if your user, if your DB has 100 million records in it, 100 million records in it, and when we go ahead and store it in 10 different individual smaller subcomponents, we will have some techniques to store it in 10 different subcomponents, and this is called a sharding, wherein, say, the user 1 till 10 million will be stored in the first shard, and the user 2 till 20 million will be stored in the second shard. Shard is just a smaller manageable chunk, wherein the retrieval or the read rate will be much faster. This will be like distributed across multiple servers, wherein the load balancer can route the request to different shards based on the ID of the user. So eventually, this is for more speed, or when it is a very bigger and complex TP. The next one is replication. This is creating multiple different copy across nodes. Say you have an very smaller DB, but the throughput is very high for your system. If your DB is of very small size, say few MBs, then you can start keeping copies of the DB into different servers and nodes, so that uh, um, like a number of requests can be handled in very short span of time. So these are the very few terminologies that I thought we might need to give a brief intro before we deep dive into the system designs series. Hope you like this video. Um, please do subscribe. Thank you for watching.